everybody. Good afternoon, Doctor.
Yes, Fatima, how are you? Yes.
I'm fine,
Yes.
thank you. How about you?
Thank you, thank you.
Thank you. Nice to see you all in here.
Nice to see you, Fatima. How are you?
Thank you. I'm fine, Hojam. I hope everything is okay with you.
Yes, exactly.
Exactly.
Fine.
We are in the same island, so everything is same, you know, Fatima.
Yes, exactly. We are in the same situation, as you know.
Yeah.
Huriye Hocam, merhaba.
Hello, merhaba. Nice to meet you. I have heard a lot
Nice to
about
meet
you.
you in here. Thank you. Everything is fine.
Yeah.
Congratulations to you for
Thank you.
your just employee in the university.
Thank you. Many thanks. It's very nice to meet you.
Thank you. Thank you.
So, shall we start? If everyone is ready, or should we wait?
Okay.
Yes.
If everyone is ready, yes, I think we can start.
All right. So, I would like to say welcome to everyone once again. So, today Flora will be defending her master's thesis. And as you can see, her thesis title is Shadow Cast of the Schwarzschild-like Black Holes. So, unless anyone has anything to say beforehand, I would like to invite Flora to give her speech. Yes, Flora.
Yes, again, hello to everyone. And my defense title is about shadow cast of the Schwarzschild-like black hole. And today I will talk about introduction, Schwarzschild black hole, null geodesics, and shadow of the Schwarzschild black hole, quantum correct Schwarzschild black hole, and summary and conclusion. First of all, what's a black hole and why it's so important in the universe? Black holes are scary and at the same time magnificent cosmic bodies, and they seem to absorb everything in the universe. The gravity of black holes pulls so strong. From this gravity, no particles and electromagnetic radiation like light can get out. Black holes can be small, also very big. Four types of black holes have been identified: miniature, stellar, intermediate, and supermassive. The mass of the stellar can be many times greater than the mass of the Sun. In Milky Way, as these galaxies, there are maybe many stellars, and there are also in universe some black holes that masses more than 1 million suns together, and they are called supermassive. There is a supermassive black hole in the center of every large galaxy. For example, in Milky Way galaxy, it's a Sagittarius A, and it's very large, and its mass is about 4 million suns together. And the second question, how do black holes form? The most well-known way about formation of black holes is stellar death. By the end of stars' lives, most of them will swell, lose their mass, and could create white dwarf. However, the largest of these flaming objects, which at least 10 to 20 times larger than the Sun, had become either when dense neutron stars or stellar black holes. In their final stages, we know that the giant stars cause supernova. It's a powerful, bright star explosion. While the star present, nuclear fusion produced a permanent external push, and that balanced the star's internal attraction from its own mass. In the stellar remnants of a supernova, there are no longer forces resisting that gravity, and that's why the star core starts to collapse in on itself. And if its mass falls to an infinitely small point, a black hole is formed, gathering the whole mass, which is many times the mass of the Sun, into a small point, gives a black hole strong gravitational force. Some black holes are not of stellar origin, and British astrophysics Stephen Hawking suggested the existence of non-stellar black holes. According to this proposal, during the Big Bang, the mass of which is equal to or less than the mass asteroid of an asteroid might have been formed with extremely high temperatures and density. Over time, this black hole lose mass through Hawking radiation and disappear. And the next question is about what happens if something goes through the black hole, and is there a way out of the black hole? When objects like, for example, planet, spaceship, stars, even light comes too close to a black hole, they cannot escape from the strong gravity of the black hole. If they go through the black hole, everything will disappear, even if it moves at the speed of light. When stars move too close to a supermassive black hole, they can break up into very bright sparklets. Everything that crosses the event horizon of the black hole, which leads to the point where it's impossible to escape, theoretically designed for spaghettification due to the sharp increase of the gravity of black hole. To a distance observer, clocks near black hole would appear to tick more slowly than those farther away from the black hole due to this effect known as gravitational time dilation. An object falling into a black hole appears too slowly as it approaches the event horizon, taking an infinite time to reach. At the same time, all processes on this object slow down from the viewpoint of a fixed outside observer, and causing any light emitted by the object to appear rendered and dimmer, an effect known as gravitational red shift. And also, the simplest static black holes have no electric charge and angular momentum, but these black holes have mass, and according to the Carl Schwarzschild, these black holes are known as Schwarzschild black holes, who found this solution in 1916. Here is described separately about structure of a black hole. In this picture, first of all, you can see at the center of a black hole singularity. A singularity, the whole mass of the black hole is concentrated here. And gravitational singularity at the center of a black hole is a region where the space-time curvature is infinite. And next one, you can see photon sphere. Photon sphere is the outer edge of the black hole where the light bends but can still escape. And photon sphere is a spherical boundary of zero thickness. Photons move on tangent to that sphere, are caught in a circular orbit around the black hole, and event horizon, it's a point of no return around the black hole. And according to the general relativity, the existence of mass deforms space-time. The path bends through which the particles pass bend towards the mass. This deformation is very strong on the event horizon of the black hole, that there are no ways to run away from the black hole. And accretion disk, it's a disk of dust, gas, planets, and stars which fall into the orbit of a black hole. Matter falling into a black hole can form an outward accretion disk, and this disk heated by friction and forms some of the brightest object quarks in the universe. And in this slide, I give a little information about the history of black hole. In 1915, Albert Einstein developed his theory of general relativity, showing that gravity affects the motion of light. After finding an exact solution to Einstein approximations of general relativity, a German astronomer and physicist Carl Schwarzschild proposes a modern solution of a black hole. In 1958, the Schwarzschild surface was identified as an event horizon by David Finkelstein, and for the first time he published there is a region of space where nothing can run away. In 1963, Royke solved the equations of general relativity which described rotating black hole, and in 1967 the term black hole was invented by American astronomer John Wheeler. In the same year, Bernal discovered pulsars, and until 1969 it was shown that there were fast rotating neutrons there. In 1971, some researchers independently identified Cygnus X1. It was the first known black hole, and from 209 to 2017, the event horizon observations reveal image of the M87 black holes. In April 2017, the Event Horizon Telescope captures the first detailed images of the shadow of a black hole. And in June 2021, for the first time, the light from behind a black hole was observed by scientists. I like to give a little information about what is the Event Horizon Telescope. It was designed to capture images of a black hole. And the main goal of Event Horizon Telescope to catch international collaboration from a Planck scale, which consists of 8 ground-based radio telescopes. And in this chapter, I will talk about Schwarzschild black hole. The simplest black hole solution is described by the Schwarzschild geometry. The Schwarzschild solution in Schwarzschild coordinates ds squared equal, you can see here equation 2.1. Here m the mass of the black hole and bigger than 0. For 0 less than r and r less than 2m, this metric is also a solution of the vacuum Einstein equation, and r equal to m is a Schwarzschild radius. If r bigger than 2m, the Schwarzschild solution is static. And here I mention about theorem Birkhoff. Any spherically symmetric solution of the vacuum Einstein equation is isometric to the Schwarzschild solution. This theorem implies that the space-time outside any spherical body is described by the time-independent Schwarzschild solution. And solution found the Schwarzschild found the solution, and which you can see the equation 2.2, and from here the omega 2 square equal, and again you can see equation 2.3. It's a line element on the sphere S square, and Fr equal 1 minus 2gm over r, and if Fr equals 0, from here r equal 2gm equal r plus, it's called the horizon. And the next step, I equalize the equation 2.4 right side and equation 2.5 right side. If equal each other, from here Newtonian potential Vr equal gm over r. And it's a Newtonian potential. In the Schwarzschild solution, if r goes to 0, you can see this from equation 2.4. If r goes 0, if r goes infinity, which is a true singularity, and inside the horizon, which means r minus less than r plus, the even light cannot run away. And to determine tau equal it, thus Minkowski space becomes Euclidean, and ds square equal d tau square plus dx square, and the Schwarzschild metric ds square approximately equal, I wrote here equation 2.9. If r equal r plus epsilon, it's outside but close to the horizon, epsilon bigger than 0, then you can see the equation 2.10. And Gibson and tau are completely independent of omega, so the space near the horizon separates into a sphere S square of radius r plus and a two-dimensional manifold of metric. Then you can see equation 211. And if the coordinates are changed to rho and chi, then ds2 square, I can see the equation ds2 square to understand this manifold. And from here, which is similar to polar coordinates, but chi here is not restricted to be between 0 and 2p. So resulting space-time is a cone, but we want to eliminate the conical singularity. If it to be a plane, chi must be between 0 and 2p, and so must be between 0 and 2p r plus. And recall that periodic imaginary time is an attribute of statistical systems of temperature, which is a inverse period. Then you can see the temperature of the black hole in equation 2.13. And since, which I mentioned it before, r plus equal 2gm, then you can see again the equation of temperature. of the black hole. And in thermodynamics, du equal TdS, where U is a total energy. In this case, it must be the mass, and then you can see the equation of mass, dm equal equation 2.15, and then you can see the equations of entropy, and from its call it the Benkirstein-Hafking formula, and A plus the area of the horizon. And the entropy, we saw that entropy is proportional to surface area and to the square of the mass. In this case, I mean, in equation 2.14, when T goes to 0, M goes to infinity, so entropy is increasing. And the relation between temperature and mass implies that the heat capacity is given by, in equation 2.18 and then 19. Expresses an unstable thermodynamic system, then free energy F, if given by F equal half 1m, you can see the last equation. And then null geodesics and shadow of the Schwarzschild black hole. Geodesics in static spherical symmetric space timeless. Then again you can see the equation 3.1. This metric can define, for instance, a spherical star, and when Fr equal Hr equal 1 minus 2m over r, which I mentioned it before, it reduces to the Schwarzschild metric. And in the following, the Earth dependence of Fr and Hr will be omitted for convenience. For this metric, the Lagrangian for geodesic motion reduces to the form 3.2. And the momenta related with this Lagrangian are, you can see the equations Pt, Pr, P theta, and P phi. By Legendre transform, this Hamiltonian is associated with the Lagrangian, and here you can see Hamiltonian equal Lagrangian, as could be anticipated, because Lagrangian is purely kinetic. There is no potential energy contribution. Therefore, Hamiltonian equal Lagrangian. And the Lagrangian does not depend on T and phi because the metric is static and spherically symmetric. And for this reason, the T and phi gives two conserved quantities, energy and angular momentum. And there you can see the equations. And the radial equation, here I wrote in 3.10, and the remaining equation leads to the equation 3.11. And if we choose, for example, theta equal p over 2 and theta dot equals 0 and theta dot double dot equals 0, and the orbit will be confined to the equatorial plane. And in conclusion, phi t dot equal E, then r square phi dot equal L. If there are massive particles, and here we know that E is energy and L orbital angular momentum. If there are two massive particles, E and L should be explained like the particle energy and orbital angular momentum per unit rest mass. And the constants of the Lagrangian now means, here you can see the equation 3.14, and where delta 1 is a constant equals 0 for null orbits, and delta 1 equals 1 for time-like orbits. And this is familiar effective potential equation used to study the qualitative features of geodesic motion. Then R dot square equal VR, and VR equal the equation of VR you also can see in 3.16. Effective potential for Newtonian orbits. In Newtonian mechanics, in spherical coordinates, the total energy equal kinetic energy plus potential energy. In three-dimensional non-relativistic mechanics, V square equal x dot square plus y dot square plus z dot square, where x dot equal dx over dt, and so on. Here x equal, I wrote here the equations of x, y, and for z, x, y, and for z. To simplify the method, the motion can be considered in the xy plane, thus z equals 0 and theta equal p over 2, theta dot equals 0. Next, I wrote here the equations for x dot, y dot, and z dot. We know it's planes. That's why that equals 0 here. And substituting this into the formula for kinetic energy, I did here some calculations, and using sinus square phi plus cosine square phi equal 1, then I get the result for kinetic energy. You can see in equation 3.18. And L is the angular momentum. If I use these equations, the total energy, you can see here 3.19, the equation for the energy, total energy. Since L phi dot equal L over mr, here I wrote two different forms energy. The equation 3.20 and 21, it's for energy equation, and then the equation for effective potential. You see here the value of doing this is that we are very familiar these solutions. Thus we have written the equation of motion as a one-dimensional equation in a radial coordinate r with energy, kinetic energy plus potential energy. But the value of doing this is that we are very familiar the solutions of a one-dimensional equation for a particle moving a potential well. And in this slide, the right side, you can see plot, but and I will explain this plot. According to the total energy, the particle may run away the well and travel off to infinite, or can stay in the well and oscillate back and forth in the bottom of the well. The particle might be at rest at the bottom for small enough energy, and from the equation, we see that if R equals 0, effective energy drops from infinity, reaching R equal R minimum, and so V effective equals 0 at R equal infinity. The radius of the circular orbit is found by finding the minimum of the effective potential by solving dVf over dr equals 0. This gives us R equal Gm over V square. If total energy less than 0, thus the particle oscillates around the bottom between turning points L1 and L2, and the orbits are the elliptical Kepler orbits. If total energy bigger than 0, there are hyperbolic Kepler orbits which come in from infinity, reach the nearest approach point, and then return to infinity. At last, if total energy equals 0, the particle will do similar things. However, the orbit will be parabolic. The easiest solution to this one-dimensional problem is a particle at rest at the minimum. The particle just sits there, which means R is constant. There is a circular orbit of Kepler's law. And effective potential for Schwarzschild orbits. Let's apply the same effective potential technique to the full R geodesic equation, and then you can see the equation 3.23, and for potential energy 3.24, and from here Rs, its Schwarzschild radius, equal to Gm over C square. Then again, the right side, you can see the plot, and I will explain which its orbits. First of all, one, it's a bound circular orbit at the minimum, and radius determined from dVf over dr equals 0. And two, there are also the bound orbits with turning points R1 and R2, as in the Newtonian case, but not elliptical. And three, the orbits that start at R equal infinity to reach a distance of nearest approach and get out again as for Newtonian hyperbolic orbit. If differentiate and set to 0, the maximum point can be found on the top of the hill. Since the slope is 0 here, the particle will remain on top of the hill if it carefully balances there. So this is unstable circular orbit, and if a particle is affected to the outward a little, the particle will run away to infinity. On the contrary, if a particle is affected to the inward a little, the particle will fall in the hole. And 5, the capture orbit is another new type of orbit which not found in the Newtonian case. The particle passes through the highest point and then falls into the hole as so not to return. This can happen when the energy is high enough. And to find the radius of the circular orbit, first of all, I wrote here the equation of potential energy, then differentiate and set to 0, and can be simplified this to a quadratic equation in R by multiplying through by mr to the power 4. Then I wrote the equation 3.27, and there are two solutions, R plus and R minus, and from this equation we see that there are no real solution when the quantity in the square root is negative. So in that case, there is no circular orbit. If there are two solutions, means two circular orbits at different radius if when the quantity square root is positive. So two circular orbit solutions were obtained if L square bigger than 3R S square, M square, C square, and none if not. By taking the second derivative, it can give information about whether the orbits are stable or unstable. If a second derivative bigger than 0, it's stable. If second derivative less than 0, it's unstable. And if the square root term vanishes, the smallest possible stable circular orbit will happen. If L square equals 3R S square, M square, C square, it will be obtained. In this case, a minimal stable circular orbit R minimum equals 3RS. That's exactly 3 times the Schwarzschild radius. To check whether the orbit is stable or unstable, again, I wrote the equation 3.30 and equals 0. So this is neutral, means neither stable nor unstable. Schwarzschild black hole. In Schwarzschild black holes, which I mentioned before, Fr equal HR equal 1 minus 2m over R, the radial equation reduces to R dot square. Then Carl rewrites this equation in a form meant to stress the Newtonian limit. Then you can see equation 3.32, where epsilon equal y square over 2. And then you can see the equation of potential energy. And a more conventional choice, Shapiro and Tsiolkovsky or Misner, Torne, Wheeler, is to write the equation 3.34, and then you can see the effective potential for particles in equation 3.35 and effective potentials for photons. And the motion of photons depends only on the impact parameter, B equal L over E, and then you can see orbit equation and effective, then the equation of effective potential. The circular orbit corresponds to the equation 3.39. Because of the spherical symmetry or circular orbits form a closed surface, which is so-called Photon Sphere, whose radius is determined by the equation 3.40. The standard shadow radius is given by corresponding impact parameter BC, and I wrote the equation 3.41. And in here, in figures, the left side, effective potential for photons, the appropriate critical impact parameter to the light ring separates plugging in the orbits from scattering orbits, and right figure about effective potential for massive particles. Circular geodesics in the Schwarzschild metric. By definition, circular geodesics have constant real radius coordinates R, and R dot equals 0 and R double dot equals 0, which the second condition ensuring that circular orbits remain circular. And I here recalled the equations which I mentioned before, and from this equation VR equal VR prime equals 0, the condition VR Schwarzschild prime equals 0 is equivalent to the equation 3.42. Two results can be drawn from this equality. Circular geodesics exists just for R bigger than or equal to 3m. Now circular geodesics delta 1 equals 0 exists just at R equals 3m. And the angular frequency of the circular orbit is omega c. And then I wrote the equation for L square. And the condition VR equals 0 translates to the equation 3.45. As a result, relativistic analog of Kepler's law, omega c square equal m over r cubed. And then you can see the VR Schwarzschild double prime, the equation for VR Schwarzschild double prime. And from here, with r bigger than or equal 6m, circular geodesics are stable. And therefore, r equals 6m is called innermost stable circular orbit. With 3m less than r or equal r and r less than 6m, circular geodesics are all unstable. Again, we recall the effective potential for geodesic motion. The extreme situation should be considered. Two extreme situations should be considered. First of all, E equal 1 and E goes infinity, the ultrarelativistic limit. The second situation is compatible to massless ultrarelativistic particles, so delta 1 equals 0. If E equal 1, for example, particles dropped from rest at infinity, there is you can see the equation for r dot square. And there is a turning point, for example, a real value for r for r dot, and just if L over m square minus 16 bigger than 0. In addition, all turning points are located at r equal r plus equal 2m. It's out the horizon. It leads to the critical angular momentum for capture is L critic equal 4m. To capture of massless particles, delta 1 equals 0, determining an impact parameter B equal L over E, then you can see the equation for r dot square. To find the turning points, we must now solve a cubic equation. Following Chandrasekhar, we look for the critical B such that the cubic polynomial 3.51 has no real positive roots. It's clear that the roots R1, R2, R3 of the polynomial ensure R1 plus R2 plus R3 equal minus B over A, and R1, R2, R3 equal minus D over A. And therefore, we know that there is always one negative root because the polynomial tends to minus infinity as r goes to minus infinity, and it's positive equal to 2mb squared at r equals 0. And there are therefore we have two possibilities: one real negative root and two complex conjugate roots, or one real negative root and two distinct real roots. And then I wrote here the equation 3.52, and from here for B critic equal 3 square root 3m and R critic equals 3m. The main results for this discussion: circular null geodesics are unstable and they are located at R equals 3m. The circular impact parameter for capture of light rays or gravitons or massless scalars are compatible exactly to this circular null geodesics. And in this figure, again, the left side, you can see about critical impact parameter. From this figure, you can see if B equal B critic, the light will collect around the black hole. If B less than B critic, the light will be absorbed by the black hole. And if B bigger than B critic, the light will escape from the black hole. And here about a shadow of the non-rotating black hole, Schwarzschild black hole, and quantum corrected Schwarzschild black hole, null geodesic in quantum corrected Schwarzschild black hole, a simple quantum corrected Schwarzschild black hole obtained by Kazakov and Solodukhin. Kazakov and Solodukhin showed that when considering spherically symmetric quantum fluctuations of a Schwarzschild black hole, the four-dimensional theory of gravity with Einstein action reduces to the effective two-dimensional dilaton gravity. And here S action And you can see the equation of action. Here UR is the dilaton potential, R to the power in brackets 2, the two-dimensional Ricci scalar, and Gn, the Newtonian constant. Schwarzschild-like metric is a solution for this action. You can see the equation for ds square, and Fr equal, you can see for 4.34 Vr, and then Kazakov and Solodykhin found that, Kazakov and Solodykhin found that for a normalizable potential takes the form 4.4, and GR the normalized Newton potential, and determining a new parameter A equal 4 square root GR. The metric function is obtained for a quantum corrected Schwarzschild black hole. Then you can see equation 4.5 for Fr, and for an empty space with no quantum fluctuations, Fr equal 1. UR equal 1, dilaton potential equal 1, and the metric is reduced to the Schwarzschild metric. It's not surprising, since a Schwarzschild metric is a unique spherically symmetric solution of Einstein equation in empty space, and a central point-like singularity of the Schwarzschild black hole, which was originally at R equals 0, is now shifted to a central two-dimensional spherical region with radius as that of the order of the Planck length. And in this sense, the quantum corrected Schwarzschild black holes renders spacetime regular. And then the horizon is located at R0, and also the metric is finite at R equal A. The curvature is divergent on this two-dimensional sphere, and this is because the reducing procedure is not a complete quantum scheme for four-dimensional gravity. And the geodesic equation describes the orbit of one particle moving in curved spacetime, which can be introduced as the Euler-Lagrange equation. From here, tau is a proper time, L is the Lagrangian, x dot to the power mu, the for velocity of the particle. The Lagrangian for line element is, here you can see in equation 4.8. And for a static spherical symmetric metric, we can always restrict the particle to move on an equatorial plane. For example, theta equal p over 2, theta dot equals 0. Furthermore, the Lagrangian does not involve coordinates t and phi explicitly, so there are two conserved quantities, energy and angular momentum. Here you can see the equations for energy and angular momentum. Then you see the equation for point 11, and from here effective potential, the energy of effective potential, and P equal L over E is the impact parameter. The circular orbit appropriates to the equation 4.13, and because of spherically symmetric or circular orbits form a closed surface, which is a so-called photon sphere, and this equation 4.14, it's the radius of photon sphere, and the standard shadow radius is given by corresponding impact parameters. The equation 4.15, it's the impact parameters, the equation of impact parameters, and it's for Schwarzschild black hole. But then for KC black hole, you can see the shadow radius for KC black hole in 3.16, and its photon sphere radius 4.16 for Kazakov and Solodykhin black hole. But BC again for Kazakov and Solodykhin black hole, but its shadow radius 4.17. And for Kazakov and Solodykhin black hole, we have reserved inequalities. You can see it in equation 4.18, and before x equal a over m, a dimensionless parameter here. And the standard shadow is suggested to be called a critical curve. For example, the shadow which mentioned in the inequalities is a critical curve. And the photon ring and lensing ring are highly associated with the critical curve BC. And in this table, I give different value to x and get result for photon sphere, but I'm fixed here, just 1 equal 1. And in this table, I again give different value to x and get the result for shadow radius. Again, I'm fixed here, equal 1. For example, for 0, 3.3, for 1, 3.69, for 2, 4.66. And its figure, shadow of the Schwarzschild light black hole for various values for A. For example, A equals 0, it's a Schwarzschild case, black, 0.5 brown, 2 blue, 3 gray, 4 purple at fixed values of GM equal M equal 1. And again, you can see here two figures. Left side, the figure shows observational appearance at the thin disk and shadow of the black hole for values of M equal G and A equal 0.5. And right side, the figure shows the photon trajectories of the Schwarzschild light black hole and again M equal G and A equal 0.5. Summary and conclusion. The main goal was here to calculate the photon sphere and shadow radius of the Schwarzschild black hole. And for this purpose, I did some stages here. And I give information about just black hole. Black hole are region of space-time where gravity is so strong, nothing can get rid of this region, hence the name black hole. And what was Schwarzschild radius? Schwarzschild black hole was static black hole. It's a black hole that without electric charge and angular momentum. And right side, you can see the equation for photon sphere and shadow radius. First of all, for Schwarzschild black hole, and in below for Kazakov and Solodukin black hole. And here I mentioned my reference. It was my defense subject. I hope I did good. Thank you for listening.
Thank you very much, Flora.
Thank you, Flora.
Thank you. I thank you. You listen me. Thank you. I take your time. Thank you.
And thank you so much. So we now start evaluating your performance. I would like to start from Mustafa Hoca, if that's okay for everyone. So Hocam, would you like to make some comments?
Okay, Flora, you have done a good job. You have studied about the spherical cases, but let me warn for a few points. First of all, the real geodesics of the Schwarzschild are not these, because everything is projected to the equatorial plane, you know, theta equals pi over 2. So I suggest you to study the geodesics when theta is not pi over 2. And then what will happen to the shadows in one more dimension of theta? You will get non-spherical things.
Yes.
Similar to rotating cases, there is some kind of deviation from spherical symmetry. So the real geodesics, even null geodesics of the Schwarzschild are much more complicated, that they are expressed in elliptic functions. So it takes much more work than what you have done. But I just suggest you to study those exact geodesics of Schwarzschild when theta is not pi over 2. So that is one point. And another point is usually you study the Schwarzschild geometry of a black hole. But suppose they ask you, what is the symmetry of this black hole? How many symmetric parameters it has? So did you think about this? If I ask you, what is the symmetry of a Schwarzschild black hole? Are you able to answer to me? If not, then just study and learn about it. Okay, because what we are doing are complete geometrical theories, so we must be able to answer to mathematical questions at the same time. Okay, when you project it to these into only the plane of theta pi over 2, you say angular momentum and the energy are conserved through like Keplerian problem, but it is more than those, So I also suggest you to study the symmetries of the Schwarzschild black hole in general, not with theta pi over 2, okay? So I do not want to ask anything more here. I can ask, but as I said, this is a master thesis. You have done a good job. You have studied good. You have presented good. So my credit is positive for you.
Thank you, Hoca. Thank you.
Thank you, Mustafa Hocam. So I think next is Fatima Hoca. Would you mind sharing your opinions with us?
Thank you, Huriye Hocam. Habib Hoca is here. Let's just listen to Habib Hoca. Thank you so much. It was nice. But let's first listen to Habib Hoca.
Habib Hocam, are you here?
Yes, I am here. Thank you very much. Actually, I am not the jury member, so I am here just to listen. So I leave the session to the main jury members. And according to me, it was perfect. Congratulations to our student Flora. She was a good student. I know her very well.
Thank
and
you, Hoca.
congratulations to Elzad Hoca also. Sorry, Ali Hoca. So anyway, I congratulate her and Ali. Hopefully she will do a better job. Actually, she will continue in the same quality, even better in her PhD. So I have nothing else to add. We can listen to the jury members. Thank you.
Thank you, Hoca.
Thank you very much.
Thank you, Hocam.
Yes, Flora, are you planning to make a PhD?
Actually, right now, no, because of the situation of disease and big economy. But in the future, I'm not sure about. I didn't, and right now, I'm not sure because I have son here, goes to school, and that's why.
Okay, so Fatma Hoca.
Okay, Flora, first I should say that you were very good student. Thank you. Everything was fine. Just I think you are Russian. Your accent was a little bit different.
No,
Am
Azerbaijan.
I right?
Azerbaijan.
Azerbaijan. Fine. Okay. Everything is okay, but if you wish, I can ask a small question. Flora, if you can, please, would you please talk about a little bit? You show some temperature, Hawking temperature there. Just I'm interested to know what you think about the unit of Hawking temperature. You know, in physics, everything, each quantity has a specific unit, okay? Like second for time, a kilogram for mass, and so on. What is a unit of Hawking temperature?
Hawking temperature, you mean?
Yes.
Temperature unit. Actually, the unit of temperature we know in Kelvin, but about Hawking temperature, I just know that Hawking radiation, it's the photons emitted by black hole, and it causes Hawking radiation. And the temperature, Hawking radiation is Hawking temperature, and I give about information here. And this temperature inverse depend on the mass of the black hole. But I think here I mentioned about temperature, but for unit of Hawking temperature, actually. Now I am a little exciting. 1 minute.
No, it's okay. It's fine. Yes, you are in right way. Thank you. It must be Kelvin and like this. Actually, about the unit of Hawking temperature, we can say that a mini black hole can has a temperature such as 1000 Kelvin. Okay, it's equivalent to the rest mass energy of a proton. So you are in right way. It's fine. Just if Professor Halil Soy has any other opinion about it, we'll listen to him.
Well, always we use geometrical units. So when you look at the expression of the Hawking temperature, it is inverse mass. And mass is length in geometrical units, so it is inverse length. But there is a point here that most of the people miss. The Hawking temperature is not a classical expression. It is a quantum expression. And when sometimes I ask, how can you show that it is a quantum expression? People should realize that there is H bar in the expression. Mm-hmm. But because we choose H bar as 1, that is why it does not appear, and it seems to be a classical expression. So therefore, we should know from if we put the complete put units, I mean H bar, C, G, everything, then you can see the units, but in the geometrical units, of course, the length, energy, these are all related. You see that R, the T is inverse mass of the Schwarzschild black hole. So in geometrical units, the unit of T is inverse mass, shortly.
Mm-hmm. Yeah, thank you, Hocam. Thank you so much.
For information. Thank you.
Okay, so I am going to close because I have a class, so if you don't mind. But Flora was very good. I congratulate her also.
Thank you.
Of course, I congratulate also Ali because of his effort.
Thank you very much, Hocam.
Okay, Hocam, thank you so much for joining the meeting. And I guess we will let Mustafa Hoca go. Then, Ali Hocam, do you have anything to add or any comment?
Yes, congratulations, Flora. You did well, and I think you studied hard in 2 years, and so you learned many things. I hope that you continue to your education, PhD, later. Maybe you can find a PhD position in the Azerbaijan, because we know that there are very good institutes and universities in Azerbaijan, in Baku. So if you find the time and money, it will be very good for you to continue your education. So congratulations again, and Cyprus and the EMU is always your home. Always, you are welcome to here.
Thank you, Hoca. Thank you.
Okay, I think I'm the last one to speak. So congratulations, Flora, one more time.
Thank you.
I have read your thesis as well, and I would like to congratulate you and your supervisor for the conducted research. There are a couple of suggestions that I wanted to add, so I'm planning to send you an email if that's fine by you, so that you can check them when you have time and apply the modifications, but just think of them as suggestions. Okay, I'm going to
thank you. Thank you.
Probably. But rather than that, I also agree with all the jury members my feedback and opinion is also positive. So I guess on behalf of the jury committee, I will just say congratulations one more time. So you are evaluated as successful by everyone. Well done.
Thank you.
And thank you, all
Thank
jury members and Haripaja for joining as well. So if there is anything else you would like to say, we can continue. If not, I guess we will end the session.
Okay, so thank you very much. Have a nice good night and see you later.
Thank you. Congratulations, Flora and Ali Hossa. One more time.
Thank you very much. Thank you very much.
Thank you, everybody. It was very nice to meet you online, of course. We missed being online. So
Yeah.
again, we are online. That's because of Flora. So again, congratulations and see you, everybody. Thank you.
Thank you.
Thank you very much, Fatma Hocam, to join us today.
See you and congratulations once more, Flora and Ali Hoja. See you later.
See you later in university.
Bye
Bye.
Bye bye. Thank you so much. See you.
See you. Bye bye.